All right, let's take a stab at this. So this is going to be the first lecture for Chemistry 441, which is Biochemistry I for University of Alaska, Anchorage. And welcome, my name is Dr. McGill. You can see that we're going to be starting with Chapter 2. Chapter 1 has a bunch of content in it that's worth perusal. I think nearly all of you has seen it before, probably multiple times. So, in a nutshell, what is in Chapter 1 is a summary of the basics of cellular biology and an introduction to the concept that there are just discrete types of macromolecules. To summarize Chapter 1, you've got, let's see here, proteins, you've got carbohydrates, you've got lipids, and you've got nucleotides. So you got your DNA, RNA. And they have discrete roles. Sometimes they have a little bit of overlap to their function, and they complement one another. And what we're really going to be doing in this first semester of biochemistry is delving in to these four subcategories of macromolecules and their structure function. So you're going to hear me use the term structure function frequently. You're going to see some slides here that say structure and function. But as you'll see as we move through the semester, the function, biological function of a macromolecule is inextricably tied to its structure. And the minor modifications to structure dictate function. Likewise, minor modifications to structure will modify the way in which a macromolecule responds to its environment or to small modifying compounds which are used to regulate them. So, that aside, that's Chapter 1 in a nutshell. Give it a run through. If you see anything that you're not familiar with, let me know, but I suspect that all of you will be more than comfortable with the content from Chapter 1. So, we're going to just jump right into Chapter 2, and you're going to see I'm going to add some extra elements that aren't included in the book because I think that we need to spend a little bit more time not just focusing on the weak interactions of aqueous systems, but also water itself, because water is a remarkably understudied and difficult to study compound which lays the foundation for all of the initial self-assembly of macromolecules, and therefore dramatically influences the way biological function happens at a chemical level. So let me just go ahead and move along. So, like the slide says, NonCovalent interactions define the structure function of biomolecules. Now, we do look at covalent bonds in macromolecules, and those are the fundamental definitions of what makes a macromolecule its unique identity. However, it's the non-covalent weak interactions within those macromolecules and between those macromolecules and each other and between those macromolecules and their environment which define the refined three-dimensional structures and the ways in which they interact with one another. So these are just a couple quick examples that elucidate that idea, but it's going to be an underlying trend throughout the entire semester. So the way in which enzymes or substrates interact with small organic compounds or lipids or carbohydrates as a detection method, for instance. If we're, I'm moving things around here. Here. When you have human growth hormone binding the receptor, it doesn't covalently associate with the receptor. What's happening is the receptor and the human growth hormone associate with each other on these chemical surfaces, and if we zoom in far enough, we're going to have those chemical interactions clearly defined by specific residues of amino acids, and that is going to dictate how the human growth hormone interacts with this receptor, therefore triggering off the signaling cascades associated with that hormone being distributed in our physiology. So this is just one example, but like we said, this is going to be a theme that you see over and over and over through the semester. So what are we talking about when we talk about non-covalent bonds or weak bonds? Well, as you can see, covalent bonds, I'm going to get the hang of this eventually, have significantly more energy associated with them than our weak bonds. And we have different varieties of weak bonds. But covalent bonds, remember, are established through the actual sharing of electrons through space between two nuclei, and this gives rise to very strong association between those nuclei. It doesn't mean that you can't break those bonds, but it takes a lot more energy to do that and to reform new bonds. Now, if you're looking physiologically, let me grab a different color here. At the amount of energy released from a single unit of ATP, you can see that if we're trying to regulate something at a chemical level in a biological system, and this is our primary source of energy as ATP, it's much easier to regulate systems when we have sufficient energy to overcome the associative nature of these weak bonds than if all of our chemistry happened via covalent bonds. In fact, we wouldn't be able to regulate our biological environment adequately. So here's a couple examples. We have, in this case, salt bridges, hydrogen bonds, Vander Waals interactions. And the salt bridge is actually just another term for a charge-charge interaction, as you can see here. And a charge-charge interaction is the interaction between two fully charged species, positive and negatively charged, and we'll get into that in the next slide a little bit more. Hydrogen bonds, we're going to go into substantially more depth on those. Hydrogen bonds, most of you are very familiar with because we've seen a lot of hydrogen bonding in organic chemistry. We've seen it as an underlying theme in how water associates with itself three-dimensionally. But we're also going to see hydrogen bonds used prolifically in establishing the larger structures, especially in proteins and in DNA. And then Vander Waals interactions are substantially less strong than both charge-charge or hydrogen bond type interactions, but they're also going to play important roles in how structures finally associate with one another. So here's a summary of different non-covalent interactions. Like I said before, we have the salt bridge or charge-charge interaction shown in A, and that is a full positive charge and a full negative charge that are established usually in biology due to the pH environment. We're going to get more into that. But because of the physiological environment, you have a positive charge on this amine, you have a negative charge on the carboxylate, and because of these opposite charges, they're going to be strongly attracted to one another when they get in proximity. Now, you also have different degrees of charges that can be attracted. You don't necessarily have to have a full complement of charges to get this kind of attraction, even though that's the strongest charge-charge interaction. You can have a charge-dipole interaction, where you can have a full charge. In this case, you have, promise I'll get the hang of this, a full positive charge, and then you have a dipole. And a dipole can be attracted to an opposite charge. So let's see if I can draw something that's representative of this. If we have, say, we'll use the water in this case. Water. Each bond within water is polar because the oxygen has a higher affinity for electrons than the hydrogen. And so it's going to have greater ownership. And in addition to that ownership of the electrons in the bond that's being shared, you also see you have the pair of lone pairs on the oxygen. And this creates an extra region of electrical density around the oxygen. And so that's going to have a partial negative charge, and we're going to have partial positive charges on the hydrogens. Now, in this case, if we have a cation, say, in this case, it's just a nitrogen with a positive charge on it, but it could be an aqueous charge. Let's say we have calcium. The calcium can have a charged dipole interaction where the positive charge from calcium interacts with the partial negative charge from the dipole in the water. And that's just something that happens all the time. You also can get dipole-dipole interactions, which are weaker still, and it's just the alignment of the partial positive to partial negative charges or vice versa. Now, another thing which we can look at in terms of types of weak interactions, which are actually really important, let me just erase all of this here, is the induction of dipole. Now, this is a scenario in which the presence of the charge next to a structure induces a dipole. So in this case, if you have an aromatic group like a benzene, if you put a charge, here we go, next to it, in this case a positive charge, it's going to cause a polarization of the electrical density in that aromatic group, and that will give you a partial negative charge in proximity. And following that induction, you're going to have an attractive event where these two things are pulled towards one another and you have an associative force. Now, once again, this is actually pretty weak. You can see through space interactions are actually quite a bit weaker here than they are here or here or here. These are listed in terms of order of strength. Now, this type of effect can take place not only in a charge-induced dipole, but a dipole-induced dipole, where a partial charge induces another partial charge. That's displayed in E. Or you can even get a dispersion force where you have a polarization due to stacking. You see this with benzene rings, and I suspect you guys saw a little bit of this in the aromatic chapter in organic chemistry too. So if you haven't seen that in organic chemistry too, go ahead and just take a look at it. Look it up, and it's not too much, and we don't go into that much detail, and it happens occasionally in the interior of proteins, and we use that as an explanatory tool for certain effects throughout when we get to the protein chapter, but it's not something we lean on that heavily. And then lastly in this list, but not least, of course, is hydrogen bonds. So hydrogen bond is where we have a hydrogen which has a partial positive charge and another group, in this case displayed as an oxygen carbonyl group, which has partial negative charge, and they associate. And the hydrogen bond isn't just a charge-charge interaction. We're going to go into quite a bit of detail here on why it's stronger, why it has a fixed length, or a nearly fixed length, and it has unique geometry associated with it as well. So we're going to get into that in more detail, so I don't want to go down that path too far. So let's keep moving on. Okay. So this is just a slide which gives us a little bit of clarification on permanent versus induced dipoles, and I talked about it a little bit in the previous slide, but it's worth taking another look at it here. On the left, you have examples of permanent versus, on the right, we have induced dipoles. And a permanent dipole, the dipole is always in place due to a difference in the electronegativity of the different nuclei that span shared pair of electrons, or in the case above with carbon monoxide, 3 shared pair of electrons. And in this case, because the oxygen here is substantially more electronegative than the carbon, it's going to have greater ownership and therefore will have a partial negative charge. Conversely, it's going to pull that electrical density away from the carbon, providing carbon with a partial positive charge. And you see that's with the water below as well, which I illustrated previously. So before we don't want to linger too long on this slide. It's just a nice elaboration on what we saw before. Now, charge-charge interactions are very dependent on the space, the proximity between them. So, in one sense, and this, don't be intimidated by this. This is just a simple equation, and we're looking at force, or the attractive force between two charges, if we're looking at opposite charge-charge interactions, is defined by the magnitude of the charges. So we have these two charges here, Q1 and Q2. Those are our two magnitudes. It would be, +1 or +2, -1, -2. And then a constant K, and the distance. And this is the really big thing I want to talk about here, is the distance. Because the distance is really important in how these charges experiencing the effects of each other. If you get them close to one another, you're going to see a pretty substantial attractive force between the charges. If you have them far enough apart, they're just not going to interact with each other at all. And one other variable that's worth looking at here is modifications of how charges interact in different solutions or mediums. And that is modified by this term here, the dielectric constant. And that dielectric constant quenches some of the effects of these charge-charge interactions. So depending on the type of solution that you're putting these two charges in proximity in, is going to dramatically change the way the charges interact. So you get some biological controls over charge-charge interactions based on the type of solution the body is creating for it. Now, on the other side of that, not just getting them close, you can't get them too close because of van der Waals radii. Now, van der Waals radii is really just defined by where the electrons typically reside in proximity around a nuclei. And we know that we can't pack electrons in too closely together because of like charge interactions. You don't want to put two negative sides of a magnet close to each other. It takes a lot of force. And likewise, we don't try to put occupied electrical orbitals together if they're not being shared in a hybridized system. So if we look at two nuclei which have defined radii, we can have these radii here, 1 and 2. There's a butter zone where the amount of attraction you're getting, as shown on this red line, increases more and 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 more as they get close together. But then as they get too close together, they get a repulsive force, and you get a certain point where you're just not going to put them any closer together. And that we often talk about in proteins as how tightly something is packed in a macrostructure. So we have two interacting components here. You want them to be close enough where you can have an attractive force, but you can't get them so closely packed that you're interfering with van der Waals radii. Okay, so now moving on to some of the meatier stuff. Hydrogen bonding. Hydrogen bonding involves a hydrogen bond donor and a hydrogen bond acceptor. And that is a little bit counterintuitive in terminology because in this case, we have a hydroxyl group, which is our donor, and here we have a carboxyl group acting as our receptor. Now, if we're talking about this in organic chemistry terms, let me just grab a different color here, and we were drawing a mechanism, we'll put in our lone pairs, and then we'll throw in our hydroxyl group. And we're doing a reaction in which we were pulling the proton off this hydroxyl group. We would start with the electrons moving towards the hydrogen, and then that breaks the bond and pushes the electrons to the oxygen, creating a new ion. Now, I don't know how that disappeared. Now, in organic chemistry terms, this would be the donor to the bond, this would be the receptor for the bond. But in terms of hydrogen bonding, it's all about what has the hydrogen attached to it. So if it has the hydrogen attached to it, it's the donor for the hydrogen bond. And if it's receiving the hydrogen, it's the acceptor. So if you think of it in those terms, it's actually pretty straightforward. Don't try to get it confused with bond origination in terms of source to sink in organic chemistry terms. Now, you can see a bunch of different, here table 2.3 from your book, a bunch of different functional groups can participate in hydrogen bonding. It's not always oxygens and hydrogens. Now, it frequently is, but we can have hydrogen to oxygen here. We can have hydrogen to oxygen in a carbonyl. You can have a hydrogen that's attached to a nitrogen. You can see all these different permutations, and you can also hydrogen bond between a nitrogen-based hydrogen and a sulfur. So there's a lot of different varieties to this, but the common thread is that you have to have a hydrogen. And we're going to talk a little bit more about why that is. Let me move along here. Now, hydrogen bonding is a pretty strong bond for a weak bond. It's not anywhere in the same ballpark as a covalent bond as a full covalent bond. Let me elaborate. And the reason I have to say that is because it's not purely electrostatic interaction. It's not just two permanent dipoles associating through space, because that's electrostatic purely. What we know, I'm going to skip right down to the meat of it, is that hydrogen bonds have about 10% covalent character. That means that there is actually some electron sharing taking place between the nuclei, almost like a partial bond being formed. And because of this, there's a necessity for orientation of the orbitals between the nuclei. And this dictates a very specific three-dimensional orientation. You want to have as linear as possible an orientation between this nuclei and this nuclei. Let me see here if I can do this again. This nuclei and this nuclei, so that all of the electrons can share as linearly as possible through this orientation. You can see this below here. We have your oxygens here and here, or your oxygen here and here. You can see this nice long linear orientation with the hydrogen in the middle and all of the orbitals aligned. Now, you can get some distortion. Like you can see here, you have some distortion from that. You have some capacity for distortion, but you want to have a nice straight line between your oxygens. So you have a linear alignment of your orbitals and antibonding orbitals, because you have to put the electrons someplace. Now, one thing that you'll see used interchangeably, and it was probably used interchangeably in organic chemistry as well, is the terminology around a hydronium. So, hydronium, a lot of the time I'll display a free proton as such. But in an aqueous system, free protons don't technically exist because they so strongly associate with water, where if you have a proton, let's say free acid, and you have water, this is going to immediately reach out with one of those lone pairs, grab your acid, and you're going to end up with a positively charged. That is a terrible positive charge. Let me see if I can fix that. Positively charged hydronium. Now, it behaves exactly the same mechanistically, because anything that's nucleophilic can still swoop in, grab a proton, push the electrons back, and you have water kicked off. So mechanistically, there's no difference. But it's worth pointing this phenomenon out, because what's fundamentally happening when you have an association of waters with one another is the ability to spontaneously form pairs of hydroniums and hydroxides. Okay, so sliding on down, we've been talking about the basics of hydrogen bonding. Let's take a look at how hydrogen bonding can affect biological molecules. So, this is sarcastic, by the way. Oh, I want to get the hang of this. That's a joke, because it happens prevalently in biological systems, obviously, and it's essential for protein structure function, DNA structure function, and the interaction of all macromolecules with their aqueous environments and with one another. So, that said, this is just an example of how you can get a secondary helical structure because of the interactions, in this case of oxygens and hydrogens, in a fashion that twists things into a helical structure. So this is just an example. We don't need to focus on it too much. But what is neat is that we spend a lot of energy on these structures and the hydrogen bond that takes place within them, but then we throw some water in the mix, and if you expose some of these structures, which are commonly housed internally, if water or some other hydrogen bondable solvent or system can approach close enough to existing hydrogen bonds, it can compete for hydrogen bonding locations. So we're going to see how solvents can disrupt some of these stable motifs that we see in proteins, and we're also going to see how proteins guard against this by having a lot of these structures at the interior of collapsed proteins. But once again, these are just previews for how we're going to see these things repeatedly throughout the semester. Now, a couple basics of water that we have to go over again. Water has the ability to participate in a substantial amount of hydrogen bonding. It doesn't commonly participate in 4 hydrogen bonds simultaneously, because that would be an enormous separation of charge. But it has the ability to donate 2 hydrogen bonds as well as accept 2 hydrogen bonds. So if I just draw the structure of water for everybody, we got our 2 lone pairs. We have our 2 donor sites, and we have our 2 receptor sites for hydrogen bonding. And we have a nice permanent dipole. And what else is unique about water is because of its ability to hydrogen bond so commonly, it bonds with itself. And this creates a very high heat capacity. It creates a unusual density characteristic for its size. When you look at something like methane or ammonia, small organic compounds that have similar sizes and masses, these typically at the same temperatures are going to be gases. It's unusual to see something that's so light as water exist as a liquid in the conditions under which it exists as a liquid. It also has a high dielectric constant. So these are some of the unique characteristics associated with water. And I just alluded to this, but these unique characteristics give it unique physical characteristics as well, where for having such small molecular weights, let me zoom in on this, where you have grams per mole of 16, 17, 18, and 34, you have, for water, a very high melting point, a very high boiling point, and a pretty darn high heat of vaporization associated with it. And the reason you see a medium heat of association associated with ammonia is because it can also hydrogen bond. It has 3 donors and 1 receptor, however, so it doesn't do it quite as well as water does. Okay, now let's look at water as a dynamic system. And when I said on the very first slide that water is very poorly understood, it's because it's incredibly difficult to study. It's such a dynamic system, and you can't probe it effectively. The minute you start to put covalent modifications on it, it's no longer behaving as water does. So seeing how water actually behaves is very difficult, and that's really challenging because what we spend a lot of time doing in biochemistry is trying to determine how biological compounds function in water and what's driving those systems. So let's start with its most basic example, where water is an ice. So in this case, in its solid form. And you see a network here in this figure below of hydrogen bond donation and hydrogen bond acceptation, and this is cooperative. As you're accepting and donating, this actually increases the relative degree of dipole so that it enhances the strength of the system. And like we said before, you have the ability to form 4 different hydrogen bonds per water, and you actually see this in ice in this extended lattice structure. Now, one of the reasons, all you guys at this point know that frozen water as ice is less dense than liquid, and that's why it floats, which is unique because usually when something freezes, it contracts and sinks. But the reason it's got a lower density in its solid form is because as it freezes, it locks in place more of these hydrogen bonds, and it locks them in at fixed distances, creating this open lattice. And this creates a uniform crystalline structure, which is less dense than the liquid. If we look over here at the liquid, these hydrogen bonds only exist transiently. They're very, very, very short in their duration. They'll bond, break, rebond on a picosecond scale, and there's only about 15% of the hydrogen bonding present in liquid water as there is in ice. So this is a rapidly fluctuating dynamic system where these bonds are sliding in and around each other and associating and dissociating rapidly. Now, it gets a lot more complex when we start to put things into this dynamic hydrogen bonding system because of basic thermodynamics associated with putting non-soluble or soluble compounds into water. So when you put a hydrophobic compound, let me do this, and to remind everybody, hydrophobic compounds don't particularly like water, therefore they're phobic of it. Like we could just say dissolved methane. That looks like there we go. This is obviously not methane, this is a more complex structure, but anything hydrophobic. What's going to happen is it's going to have a very limited solubility in water. And what water will do is to reduce the interaction with the thing that it doesn't like. It will strongly associate with itself via hydrogen bonding in a network of bonds, forming a shell around the hydrophobic compound. And this is called a clathrate. So a clathrate, and this isn't rigid bonds, remember. These are still hydrogen bonds, and they can break and reform, but this structure is more stable than the dynamic structure we referenced prior. And this, if you're thinking in terms of thermodynamics, is not a favorable interaction because it's an organization. It's a reduction of randomness. And if you're thinking about entropy, remember, entropy tends to increase. You want to see in classic thermodynamics a tendency towards disorder or an increase in entropy. So what this is, by the introduction of a hydrophobic compound into an aqueous solution, it decreases entropy and therefore is not thermodynamically favorable. This is really important though, because this lack of favorability leads to spontaneous organization of these hydrophobic components in aqueous solution. It's actually called the hydrophobic effect. And what this does is it stabilizes protein structure. It leads to the spontaneous aggregation of lipids in aqueous solutions. And we're going to look at those in substantial depth in the proteins chapter and in the lipids chapter. But we're going to look at it in a little bit more depth following here. So, you're going to see a lot of people use both these terms interchangeably, amphiphilic and amphipathic. They really are synonyms. They both mean fundamentally that in the case of amphipathic, a molecule contains both a polar and a non-polar group. In this case, we're looking at a fatty acid. Let me get everybody oriented. So here we have a fatty acid, and you have this long chain of, in this case, saturated carbon-hydrogen bonds. And in the end, you've got carboxylate, which are these two oxygens here. Now, you can get variations on the theme, but in the case of these fatty acids, we have a hydrophilic group and a long hydrophobic group. So the presence of the group is amphipathy. Amphiphilicity is how they interact with a polar or nonpolar environment, which is generalizably interchangeable. So don't be surprised to hear them used back and forth interchangeably. One is not necessarily more correct than another. And the reason we're introducing this is because of spontaneous formation of lipids into macrostructures. So simplifying everything, you can see over here we have a fatty acid, super simplified, where we have the non-polar tail, that long chain of carbons, and then we have the polar head group, which is typically, for our basic fatty acid, just a carboxylate. And moving back to the clathrate illustration, you can see, let me get everybody oriented here. On the ends of each of these, we do have our polar groups here and here and here, and you can actually get substantial hydrogen bonding between water in an aqueous environment and these carboxylates. No problem there. So you have a nice positive interaction there. But we're also getting these extended clathrate structures wrapping around the lipid. And if the lipids stay separate from one another, like here, where we have 1, 2, 3, 4 lipids in solution, more of the water molecules are occupied in clathrates. And this is a significant reduction in the entropy of the system, and that is not favorable. So what happens is, to reduce that lack of favorability thermodynamically, is the lipids spontaneously will associate with one another, and this still gets wrapped in a clathrate. But the amount of water that is sequestered in a semi-rigid clathrate structure is significantly lower because of the changed surface area to volume ratio of the aggregated lipids versus the individual lipids. And this, so when we talk about in basic chemistry and organic chemistry, biologically, fatty things like fatty things and aqueous things like aqueous things, that's an oversimplification for biological purposes, because it's not a matter of them liking each other in terms of their attraction for one another, as much as the thermodynamics of putting a non-polar compound into a polar solvent, specifically water, leads to a thermodynamic incentive for the aggregation of those non-polar compounds. And we see that a bunch of different ways. We can see that, let me grab a different color, as a micelle, where you don't have an interior, where all the tails of lipids pointed towards one another. We can have a bilayer, where we have polar head groups on the inside and outside, with the lipid tails facing each other in the middle. And you can also just get a surface of lipid, which is just, in this case, oil floating on water. But this is the primary thermodynamic force which causes spontaneous formation of membranes. And this is something that life capitalized on a long, long time ago. So, let's see what we have next. Okay, now we got to move on a little bit into acid and bases, and weak acids and weak bases, and how they interact in water, and how protons move in aqueous solutions. Because one thing we're going to see a lot next semester are proton pumps. You've probably heard of those things. It's what allows you to make stomach acid, for instance. It allows you to establish pH gradients on opposite ends of the mitochondrial membranes. There's a lot of biological functions that are essential that require proton pumps. Now, what differentiates a proton pump from another cationic pump is the high mobility of protons in solution. Now, if you want to move a calcium, for instance, so I've got this calcium floating around in solution. The only way I can move that calcium is to take it and physically move it through space in solution to another location. Now, with protons, you get a cheat. And the really nice thing about this cheat is that here we have, let's say, a hydronium. So we have an acid on this side of the system. It can interact with water here. And this hydrogen can jump to this oxygen. And let me show you that mechanistically, because it's worth going into. Now, we're talking about hydrogen bond donors, right? But if you have a hydronium, we've got our water. The water's lone pair can grab that proton, pushing these electrons to the oxygen, satisfying that positive charge. We have a nice source to sequence series here. And this is reversible, so I should have double-sided arrow. And then this first compound, this guy over here, is now just a water. And this guy over here is now a hydronium. And so what we've effectively done is by breaking a bond and forming a bond through hydrogen bonds, which have 10% covalent character, it's not much of a stretch to squeeze them together and cause an actual formation of a legitimate bond when it's water to water, can move this acidic proton to a different nuclei. And so what we've done, instead of taking a calcium, for instance, and moving it through space, we're having this nice extended chain of hydrogen bonds, and we can make that chain of hydrogen bonds be a rapid transition of an acidic proton between oxygen nuclei through solution, so that at the end it comes out the other side forming acid over here. So we've effectively moved, let me clarify that, we've effectively moved a pick a new color, acidic proton from here to here through hydrogen bond networks, facilitating rapid formation of new bonds and breaking new bonds, moving it from here and then kicking one off on the other side. So a proton pump doesn't necessarily need to move the same proton through space. It lets you push a proton from one side to the other. Kind of like that toy that has a bunch of balls suspended on strings, and you drop the ball on one side and it kicks the ball off on the other. Best case analogy here. Now, I mentioned the formation of hydronium and hydroxide spontaneously from water. Here we're seeing it displayed as just a proton and a hydroxide, but this can also be displayed like this. And you have to have that second water present in the equilibrium equation if you put the extra water here, but it's not a big deal. Moving on. So, pH. We're going to be paying a lot of attention to pH throughout the semester, because pH will dictate degrees of relative charge on the R groups of amino acid residues and proteins, which will significantly change the protein's surface chemistries, their solubilities, the way they interact with one another, etc. So we're going to have to pay quite a bit of attention to pH. And remember, pH is just an expression of the concentration of protons in solution, or hydronium in solution. And it's on a log scale because it can be a substantial range. We don't want, so for pH 7, for negative log base 10 of concentration of protons, that's what we're looking at. For pH 1, which is acidic, because a low pH means increased acidity, you have substantially more protons. And when we are alkaline, we have very, very few protons. So neutral being pH 7 in the middle. We can evaluate or predict how a system of pH will change using the Henderson-Hasselbalch equation. And really, really useful. So whenever we have a system where we're evaluating the K of that system, or the equilibrium or acid equilibrium of that system based on, let me see here, instead of just pointing at it, I'll actually circle it for you. Any weak acid where you have a generic acid bound to its proton can be an equilibrium where, I'll just write this here, where we have our weak acid here. And then over here, we have our proton, and we've got our conjugate base. And this is just, and our free proton. We can describe this expression with this equilibrium equation, where the products, the proton and the conjugate base, are over the concentration of the weak acid in solution. Now, if we want to ever evaluate this ratio of conjugate base to weak acid at any particular pH, all we need to know is the pKa, which is the same thing as the Ka, except that pKa is the negative log of the Ka. And we can move back and forth within the system predictively. So let's see if we have some good, we'll have some good examples of this. This is just a bunch of common weak acid conjugate base pairs that you'll see in biological systems. You'll see formic acid formate, acetic acid acetate, lactic acid lactate. And one of the things you'll notice throughout the semester is that we'll have a lot of 8s. So, whereas usually you'll hear lactic acid being used colloquially, in biochemistry we almost always refer to it as lactate. And the reason we do that is because when you put lactic acid into biological pH, it loses its proton predominantly, and therefore its predominant species in biological solutions is lactate. So we actually refer to it appropriately as the ion when it's existing in our bodies, versus, the physiology people who would say, oh, lactic acid production. Yeah, you're producing it, but it's existing as lactate. So, and you can see that they have these unique pKa's for each of these pairings, which describes the ratio of the conjugate base to the weak acid in solution. And this is a little bit advanced, but we're going to spend a lot more time here. This is an allusion to why this is so important. When you put a weak acid, I'm dragging things where they shouldn't be. Let me move this back up here. When you put a weak acid into solution and it partially dissociates into the free proton plus the conjugate base, what's happening is this is going to be defined by your pKa. Now, based on Le Chatelier's principle, if we add or remove protons, that can drive the equilibrium one way or the other, right? So what we're fundamentally doing, if we put a weak acid into an acidic solution, a more acidic solution, is we're adding protons here, which drives the equilibrium this direction. If we put it in a basic solution and pull those protons out of solution, Le Chatelier's principle dictates that the equilibrium will shift towards products, and you'll get an accumulation of the conjugate base at the expense of the presence of the weak acid. Now, this can be thought of as a equilibrium system being driven by Le Chatelier's principle, or you can think of it in terms of pretty common sense characteristics. If you put a weak acid in a very acidic solution, will that weak acid act as an acid in that solution? It won't. It's going to act more like the base and not have particularly tendency to to push off this proton. Whereas, in other words, the very acidic solution will be contributing its proton towards the weak acid, and that's going to favor the presence of the weak acid in its acid form. Oppositely, if you have a solution which is more basic, where the pH is higher than the pKa, so in this case, the pH is higher than the pKa of the system. In this case, the pH is, oh, excuse me, woo, bad instructor. The pH is lower, therefore more acidic. In this case, the pH is higher, therefore more basic than the pKa. Then the acid will act as the acid, donating its proton to the solution, and that will favor the production of the conjugate. So the reason this is important is because you'll see here, in this case, there's no charge. In this case, we have a charge. And the presence of that charge is incredibly important because if you have a weak acid on the surface of a biological compound, it has the ability to be protonated or deprotonated, charged or not charged. And the presence of charge on the surface will dramatically change the biological function. So we're going to spend a lot of time in the proteins chapter evaluating this, and this is just looking at how the surface charge of this particular protein varies under different pHs to illustrate how different the surface chemistry would be at pH 4 versus pH 11 versus biological pH, which is close to 6.8. So, just sneak previews for everybody moving forward and to get everybody aware of the things that are coming up. Okay. So I've been talking about pHs and pKas. Some people can have that automatically, but for some people it's been a while since you've had Chem 106, right? So it's okay to chuckle a little bit or to cry a little bit when I say that. It's all right, but you'll relearn it really fast. You thought it was over, but it's not over. So remember, the pH of the solution is defined by the negative log of the concentration of the protons. The pKa is the negative log of the Ka, and the Ka is simply the ratio of the products over the reactants in an acid-base equilibrium system. That's all it is. And here, to review, we've got that Henderson-Hasselbalch equation. Now, generalizably, when the concentration of our conjugate base is equal to the weak acid HA, that's going to happen when the pH equals the pKa. So if you have a pKa of an acid and it's 4.76, and you put it in a solution that is also exactly 4.76, what you'll get is a 50-50 ratio of the acid to the conjugate base in solution. You'll also have an equal concentration of free proton being contributed from that weak acid. Now, if the pH is greater than the pKa, let's move over here. What you'll see is a tendency for the conjugate base concentration to be greater than the concentration of the weak acid in solution. Now, does that make sense from based what we've already talked about? It does. Once again, when pH is higher than pKa, what that means is that the pH of the solution is more basic than the weak acid. So, if the pH of the solution is more basic than the acid is free to act as an acid and give its proton to that basic system. This should favor the production of the conjugate base. Conversely, when the pH is lower than the pKa, that means the pH of the solution is more acidic than the weak acid. It is therefore going to be driving protons onto the weak acid, or shifting the Le Chatelier's relationship towards the presence of the protonated acid at the expense of the production of the conjugate base. So when you see these titration curves, all you're seeing is a moles-wise addition of base, and as you add that equivalency, you're seeing a shift in pH, and we're seeing these points where you have equimolar solutions of your weak acid conjugate base, and that's taking place where the pH equals the pKa. So you can experimentally determine this through these titrations, but nearly all of these are well documented. So moving on. Buffers. Now, buffers are incredibly important because, from what we've said so far, surface chemistry is very delicate in biological systems. And if we alter the charge of residues, that dramatically changes surface chemistry, it changes solubility, it changes the way things interact with one another. So what we really have is a very small window for optimal performance of our biological molecules. We're really highly tuned machines in that regard. So what we need is a resistance to pH change so that we can continue to operate optimally and not die. And that's what buffered solutions do. And what a buffer is, anytime you have both a combination of a weak acid and its conjugate base, you have a buffered solution. Now, if you want a perfectly buffered, ideally buffered solution, you'll have them in equimolar concentrations. And you can make them by combining the weak acid with its conjugate base directly in solution, or you can titrate a strong base onto a weak acid, and at the equivalence point, you'll have a 50-50 ratio of the two. Both of those work, except that you'll have a higher salt concentration in the titration. And sometimes that's not ideal. But both of these produce buffered solutions because in the end, you have a combination of a weak acid and its conjugate. And what these do is they resist pH change, because let's take a look over here. We have our weak acid and we have our conjugate base. And if we add, let's say, hydroxide, which would increase the pH, making it more alkaline, what happens, instead of it just doing that automatically, is it interacts with the proton on our weak acid, yielding water and conjugate base. So we're producing the conjugate base. And this is much less dramatic in affecting the pH of the solution versus just having free hydroxide. And that's evident from this zone where, as you add the hydroxide, it has a very soft slope to the change of pH. Now, concurrently, if we add acid to solution, we're going to have presence of the conjugate base in the buffer. And this is going to just make some weak acid for us, which we can see here with that soft slope. Now, at the end of the day, any buffered solution has a limited capacity to buffer against change, and that's why you see that increase in slope on both sides. As you run out of buffering capacity, the rate of pH change with the addition of an acid or a base also increases. So there's details to what makes a good buffer. And the best buffered solutions resist pH change around the pKa of the buffer. So let's go back to acetic acid, for instance. Let me erase a couple things here. If we want to buffer a solution at a pH of 5. Acetic acid would be a really good buffer to do that. We could use acetic acid paired with acetate because its pKa is 4.76 or thereabouts, which puts the equivalence right there. Now, this is good because it's going to be very effective at resisting pH change on both sides of that pKa for a little bit, for about 1 pH unit. So ideally, plus or minus 1 pH unit from the pKa gives you the best buffering. You can get away with strain past that a little bit, but not that far. What's said next here is really relevant. If you are 3 pH units away from the pKa, plus or minus, doesn't matter one side or the other, you're essentially fully deprotonating or fully protonating that weak acid species or its conjugate. And we're going to go into that in the next couple of slides in terms of using equations to actually predict the degree of protonation or deprotonation. And we're going to use the Henderson-Hasselbalch for that. So let's go ahead and just jump into that. Let's see here. I don't think there's anything new in this slide. So what we're going to do, and except for that, we'll get used to the system here. This is just an illustration of our weak acid. We have our acetic acid here, and we have our acetate here, and we have our free proton. So let's go ahead and see. Oh, and they actually, look at that. They agree with me. The pKa of this is 4.76 because the equivalence point is 4.76 at pH. So here we go. So predicting pH. So to predict pH, we can just use the Henderson-Hasselbalch equation. We just need to know if we don't know the pH, we need to know the pKa of a pairing of its weak acid and its conjugate, and the relative ratios, molar ratios of the two. So if we start with a total amount of moles of 100%, and we were to add 0.1 equivalent of base to this weak acid, so in this case acetic acid, what would happen is we will consume, because we're going to be using sodium hydroxide, so we should get about 100% reaction with the weak acid, we will consume 10% of the acid form and produce the acetate. So this means that we're going to have a molar ratio of 0.1 for the acetate and 0.9 for the acid. And you can just crunch this number because pKa for the system is 4.76, and you'll see that if we were to add 0.1 equivalent of base, molar base, so let's say we have 1 mole of the acetic acid, a 1 molar solution of acetic acid, and we add 0.1 molar or moles of hydroxide, we're going to now have a 0.9 moles of acid and 0.1 moles of acetate, and we'll have this pH of 3.81. Now going the other direction, if we add more, what if we consume half of the acid? So we have 1 mole of acid in solution, and we add half a mole of hydroxide. What will happen is that hydroxide will consume the acid. Let me grab a color here. We'll consume the acid and produce the conjugate base. So what we'll have in the end, if we started with a mole of this and we add half a mole of hydroxide, we'll end up with half a mole of the acid and a half a mole of the conjugate base. And that's reflected right here in the Henderson-Hasselbalch equation. The pKa doesn't change. It stays 4.76. And the log of 1, because 0.5 divided by 0.5 is 1, is 0. Therefore, there is no change from, that's why pH equals pKa. when you have equal molar concentrations of the acid and the conjugate base. And going one step further, even though it makes sense, if we were to consume a majority of the acid by adding 0.9 equivalents of hydroxide so that we're producing predominantly conjugate base, getting out in this territory here where we're losing buffering capacity to resist pH change, pKa of 4.76 plus log base 10 of 0.9 over 0.1 is now going to give us an alkaline pH, or a pH that is more alkaline than the pKa of the acid-base pair. Now, going back to that rule, plus or minus 3 pH units. If the way it works is, let's say we've got acetic acid, sodium acetate pairing, and it has a pKa of 4.76. If we put it in a solution where the pH is 5.76, 6.76, and 7.76, what's going to happen is, here, it's 50-50 mixture if you have the pH at 4.76. But if we move the pH to 5.76, it's going to become 90% conjugate base. That is a terrible 9. Let me fix that. And that's what we're seeing here, 90%. If we take it out to pH 6.76, it's going to be 99%. If we take out another pH unit, it's going to be 99.9%. It's going to be only 1/1000th acid form, and it'll be 99.9% conjugate base form. Now, let's take this the other direction really fast. Let's say we take the pH to 3.76, 2.76, and 1.76. In these particular cases, it would be 90% acid, only 10% conjugate base. Because now the solution is more acidic than the weak acid, it's contributing the proton to the acid, and it's pushing the acidic form in the equilibrium system. If we make it more acidic, it's going to be 99% weak acid form versus conjugate form, and at 1.76, 99.9%. So we have this really cool tool for just mentally evaluating ratios based on the pH of the solution and the difference in the pH solution from the pKa. We don't necessarily have to, we need an exact calculation. This is great, but you can do it with a mental check nearly always and get a ballpark estimate of how acidic or how basic something really is, or how consumed a buffer is with a pH, with a particular acid-base pairing at any given pH. And I've had a number of people who in med school, when they're in the pharmacy programs, comment that this little quick check saved their bacon over and over and over again, and they used this little trick more than they used any other element of Biochemistry I. So I guess we can just stop now and everyone can... No, we can't stop now. We have to keep going. Okay, so I'm going to bring up a couple titrations here because we've been looking at a couple basic idealistic titrations with monoprotic acids and strong bases, and it's not always that simple. So what we do need to look at are more complex acid-base systems. And in this case, we're going to look at glycine. Glycine is our most simple amino acid. And an amino acid has the general form of an amino group in this case your NH3+. We have our acid, our carboxylic acid, COOH, and then we have our central carbon. Most amino acids have a proton, and it has an R group which modifies it. In this case, glycine has a pair of protons, which makes it the smallest, it makes it achiral, and it makes it the simplest amino acid. So we'll start with titration of glycine because it's the simplest. And because of that, we have our acidic group and our basic group. And because we have multiple weak acid, weak base systems, and we need to look at how this pair of acid bases affects the charge overall, we have a new term, PI, or isoelectric point. The isoelectric point is where we have a neutral net charge, where the amount of positive charge is balanced by the amount of negative charge in the system. Because if we are only looking at what happens when it's acidic, or more acidic, on this side of the spectrum, when it's more acidic, when the solution is more acidic, it's going to overwhelm the weak acid properties of our carboxylic acid, and it's going to keep that acid protonated, and it's also going to protonate the base. So we will have no charge on the acid, we'll have a positive charge on the base, and the net charge will be positive for the system. If we make the system more basic, thinking about equivalence of hydroxides in solution, that will deprotonate the carboxylic acid to a carboxylate, and it will also deprotonate the amino group. That will remove the charge from the amino group, but put a negative charge on the carboxylate, yielding a net negative charge under basic conditions. But when you're, kind of like Goldilocks and the Three Bears, when everything's just right, at the isoelectric point, you have neutral charge. And you can just determine that by looking at the pKa of the acid plus the pKa of the base divided by 2. No problemo. I think you guys can manage that one. This is just another way to look at it in terms of equivalency and how the species are changing as you change the pH from the isoelectric point and how it affects the charge. But you guys are free to look at this, but I don't think we need to walk through it necessarily. So we can also look at systems that are polyprotic, where you have a weak acid which has multiple weak acidic protons. Phosphate's the classic. And you go from having very acidic protons with very low, well, not very low, but fairly low pKa's of, 2.15, and then you have one at 7.2, and then you have one at 12.4. So you actually have one that's a pretty darn good biological buffer, but phosphate's a fantastic buffer over a large pH range because it has multiple buffering regions that resist pH. So this one's worth remembering. Phosphate, when you're working in biochemistry lab, will be used frequently as one of the buffering systems. Now, let me go back. Phosphate, you'll see this pKa's that are well separated. You have 2.15, and the next one 7.2. That's a pH range of 5, practically, between the pKa's. And we know from before that with that range, you're having full dissociation or full association of protons with a weak acid. So there's very little interaction of this first proton affecting the loss of the second proton. Now, if you have pKa's that are closely associated, like here, for aspartic acid, where you have a pKa of 2.1, 3.0, and then 3.9, you don't even have a full pH unit between them. So by the time that this one is 90% dissociated to the conjugate base, you still have 10% presence of this form before you even, when you're at your equivalence point for your second acidic proton. So what you get here is a flattening of the titration. And if you are doing this based on raw calculations, it's incredibly painful to work with, But if you're trying to buffer over an extended range of pH, it's fabulous. So aspartic acid, as a polyprotic acid, actually has a lovely buffering capacity right here. So let's see here. Moving on. I alluded to the beginning about how surface charge is super important on how things interact. And this is a really nice example of it. You can see where DNA has a substantial amount of surface charge, which is negatively charged, all along the surface of the DNA strands at biological pHs. This helps prevent random aggregation because it repels DNA strands from each other. At the same time, if you have a DNA molecule that's supposed to associate with a protein, you can make that happen very easily by tailoring the charge biologically along the surface of the protein so that you have this nice zone of interaction in target spots between the DNA and the protein. You see that with ribosomal interactions, even though, to be fair, ribosomes are largely nucleotides also. So that might not be the best example. Now, it's really common to use pH dependence of charge to change the solubility of proteins as part of our isolation scheme. So it's not just about biological function. In the laboratory, we have a lot of interest in actually isolating proteins. And we can do that selectively by crashing proteins out of solution. Now, my favorite example of this is not in the science lab, it's making cheese. So if you were making cheese, a basic mozzarella cheese, I mean, there's more complex ways to do it, but you squeeze lemon juice into whole milk. And what happens is you get a separation. And what happens is that acid changes the charge profile on a host of proteins, which cause them to crash out of solution. And you have your whey and you have your curds, right? Now, whey protein is the protein that stays in solution despite the acidity. And the curds contain casein, which is an insoluble protein under acidic conditions. So you can actually cause that initial separation, which leads to delicious cheeses, just by the addition of acid to milk. And this is really the same thing we do in the laboratory, but a little bit more refined, where we can use pH to alter the surface chemistries of, and you can see we have our predominantly negative charges here, a mixture of negative and positive charges here, and a predominantly positive charge on residue. And at the isoelectric point, you're going to have your optimal solubility, and then as you get increased charges, you're going to get this reduction in solubility in either direction. So this is a really neat tool that we have at our disposal, but it's also important in terms of biological function, in terms of regulating proteins or dysfunction of proteins following mutation. And we're almost to the end. It's a little bit of a long lecture, but it's okay because it's online and we can enjoy a beverage of whatever you favor, like, I don't know, tea or coffee or Red Bull or something along those lines, or something else. So here we have one of our last slides, the influence of small ions in solution on macro ion interactions. Let me go back up here. Here we can look at a couple of macro ions, where we have our protein, which has all this positive charge, and that allows it to interact on a macroscopic scale with the negative charges on the DNA. Now, that's all well and good. However, if you have other charged species in solution, and salt water is exactly that scenario where you have a bunch of cations and anions in solution, it alters the way the large ions or macro ions can interact because you get a shielding effect. A negatively charged macro ion here is going to cause a concentration of positive, which are the blue ions, around the surface of it to neutralize that charge in the system. Likewise, let me grab a different color here. If it's positive, ooh, that's the wrong choice. If it's positively charged, you're going to get an accumulation of negative charges around the surface of that macroion. And for these to interact with one another through space, there's going to be some interference of that attractive force through space when we have the presence of ions in solution. Now, in the same way, we can use the effects of pH to isolate proteins. We can also isolate proteins via techniques called salting out, where we add a lot more of these small ions to solution, and because they're going to change the surface chemistry by basically neutralizing the charge at the surface effectively, the protein will crash out of solution. Some do, some don't. It's not for all, but it's one of the techniques you can use depending on the surface chemistries of the protein. And that was the last. Let me bump up so you guys don't look at that while I'm talking. This is the last slide for Chapter 2 in terms of Chapter 2 content. What I'm going to go into next are some tools that I think I'd like you guys to go through because they're classics. I want everyone to spend a little bit of time researching the bicarbonate buffer system of blood plasma, because it's particularly relevant to what we've been speaking of buffering and the stability of biological function. Our primary system for buffering or stabilizing the pH of our blood pH is the bicarbonate buffer system. Here. However, if you look at the pKa of the system, it's 3.57, and that violates the rules of what makes a good buffer, because at a biological pH of about 6.8, that buffer is pretty much consumed, and the carbonic acid is nearly all converted to, bicarbonate is nearly all consumed to carbonic acid. So this presents a conundrum, and I want you guys to do a little bit of research. And, if you just read through here and you're pretty comfortable with, CO2, do a little reading on it. Investigate that and try to rationalize physiologically why we use this system to buffer our blood, which is such an important system, and how the role of CO2 affects it, and how our ability to regulate our intake and exhalation of CO2 can be used to rapidly adjust our blood pH. So a couple things to think on. In addition to that, take a look at this case study. It's a fabulous case study. It's one of my favorites. And try to address the questions as thoroughly as possible. And we'll pick this up at some point in the near future, but I want you to wrap your head around this one a little bit. And don't cheg it right out the gate. Actually use some thoughts. Write your thoughts down, and I know you guys will cheg it later. This one's been around for a long time. And you'll get, a thorough answer from that, but don't cheat the process. Go ahead and spend some time reading through these case studies and trying to address these questions as best as you can. Okay, so I'll just take this back to the beginning. That is it for Chapter 2, and I'm going to just leave with a couple thoughts on success in this class. Online classes are particularly challenging. It's easy to get behind. It's easy to deprioritize them, particularly for this class. We don't have a homework grade associated with this class. I'm going to assign, not assign, but provide problem sets and answers to those problem sets from a variety of sources, so you have a feel for your knowledge base. My tests are going to be a combination of basic multiple choice questions, but also short answers that will test your ability to rationalize the systems, because I'm a scientist and I want people to be able to communicate knowledge to me, not just produce an A, B, C, D, or E answer, even though we all know the answer is always C. So please take the time in your schedule, read the book first. It will make a huge difference. Detailed reading of the book first is going to make a giant difference for you. Then watch the lecture. Hopefully the lecture makes more sense of the book, don't try to use the book to make sense of the lecture, because you'll be doing back and forth. Read the book first. And stay on top of this one, because there's a lot of material on each exam, and you don't want to be behind trying to cram on it. Some people can do it successfully, but it's painful, and often that results in a grade that they're not particularly happy with. So that's it for today, and I'll be catching up with all of you next week on the next lecture.